Hello students, this is lecture number 29 and we have been studying chapters 7 and 8. So today we will talk about the numerical integration. So far what we have looked at is as far as the numerical integration is concerned, we have used the analytical integration. However, we have for this kind quadrilateral element of arbitrary shape, what we do, we convert that into a square element xi eta coordinate system from xy system, and one of the advantage here is integration. We can integrate very easily here. In this case, integration will be difficult, and this is the main advantage here. Apart from making very simple type of shape function you have in this case. The shape function what we have used, for example, is also called the tensor product method. So in which since this is becomes the element has like 90-degree angle between two sides, that makes it easily to design such a way that n1, for example, of this one we can write is as, or ni rather. So ni you can define it as n y ny I multiplied by maybe we can write is ny times nx yeah, something like this one. What is the meaning of that is okay, instead of saying is ny we can say I j n k basically, and what is the meaning of is we have two like nj we can have which denotes the linear shape function, not 2D, but we are actually making this basically. What is the we should also, I should have expanded that. So what I mean to say here is ni xi eta is a function of nj, right? Nj say this is only xi, function of xi only, and nk which is a function of eta only. So we are using basically two linear shape function. So this shape function this shape function which is linear, which may go something like this one from 1 to 0, and then this in y direction it will go 1 to 0, something like this one. From that we construct. So what is for example n1 xi eta we can this will be given by the product of two linear shape function, one in this direction. So let us say this is n1 we are talking about. So for the linear, if you are looking the this direction, we have 1 going to 0, so we can write this one is nothing but 1 minus xi, 1 minus xi, right. So from here to here we are going, and this one is minus basically, right. So in linear system, if we had say, let us say we have 0 here and L here, it would have been 1 minus x over L, but in this case we will have something different, so that minus 1 corresponds to 1 basically. Yeah. So in this case we will have something like this. We will have 1 minus okay, and maybe divided by 2. So just okay. So will be okay, let's figure out what is n like nj in this case. Okay, so let's call it 1 and 2. Yeah, 1 and 2 like this. So n1 as a function of xi in this case will be 1, which is 1 here, 0 here, and that really means something which becomes 0 here. So hence xi minus 1, of course it will be xi minus or 1 minus xi, so 1 minus xi will be that, and we know that if you put xi equal to minus 1, it becomes 2, so we have to divide it by half. So we know this becomes this. Similarly n1 2 becomes eta equal to, similar way we want 1 here and 0 there, so we will get half of 1 minus eta, and hence this will be equal to this multiplied by this one. Yeah, so you get half of n half of 1 minus xi multiplied by half of 1 minus eta. Okay, so this is how you construct it. So this makes it easier to construct that way. So you are just multiplying two linear shape function. Linear means it's a function of just xi or eta only, but not linear means 1D basically. So two 1D shape function you are multiplying together to get it. Yeah, so and this works, and we have seen that this works like that. So this is the main advantage, and so you can make even for, let us say we are talking about the 3-noded system, then what to do? Not 3-noded, 5-noded system. So you have like this one. One way is to look at the Pascal triangle. You have 1 xy x square xy y square and so on. So if you say 5 of them, so you look at 1 2 3 and then 4 5. So you will choose this, right? So you will have this, all these 5, because this is symmetric. So hence you will choose like this one. You can construct this, let's say 1 2 3 4 5. So we can say ni xy. In this case, of course you have transformed into zeta y xi and eta system. So we can simply write xi eta is equal to, you can write, either you can write in terms of like alpha, right, I plus beta I xi plus gamma I eta plus lambda I xi square plus delta I eta square. You can either write like that, then find out what is the value of this one, or we can use the tensor product method. And how we will do? So we can construct such a way that we have n xi in is equal to then we just multiply n1 xi multiplied by n2 xi n2 eta, and in this case we look at in x direction. We want something in x direction. We have 3 nodes, hence we know that we are going to find out something which is 3 which has 1 x square type of thing. Yeah. So this how we are going to find out this way, and in this way also you have 1 y square type of thing. So basically how you can do it. So there are either you can construct this way, that you have like in one direction you have this and this, you multiply them together, or here and here it has to be. So basically what I am meant to say, you can construct n1 xi in this case, let us say talking about 1. So this will be n1, so will be equal to how we are going to find out? We are going to find out this, and here it has to be 0 and here also it has to be 0, right. So either you can have like this. So xi xi multiplied by xi minus 1. So this is xi equal to 0, xi equal to minus 1, let us say. Yeah, and when you have xi equal to minus 1, then when you have xi equal to minus 1, like here, this has to be 1. So minus 1 and minus 1 minus 1, so you get 2, so you get half of this, so you get this. Yeah, so this is what you get. N1 will be like this one. Yeah, and then next one will be similarly your N2 will be also, eta will be also like half eta and eta minus 1, similar logic, and hence n1 xi eta will be equal to 1 by 4 xi eta zeta minus 1 xi minus 1 eta minus 1. So it could be something like this. So we have got this value, however, we see it has some problem. And what is the problem? You can see that the order is, you can say 4. So we have xi eta multiplied by this xi and eta this, you get xi square eta square. So this actually xi square eta square, it even down here, so it's this is not this way. So the way we have done this one, this captures something else. So what we see is we have to be careful when applying tensor product method. Okay, tensor product for, if it is for 4 nodes, we got it like this one very easily. But if you are more than 4, then we are actually not capturing the minimum order. So we should have the shape function which is of minimum order. Okay, so that way this is going to basically everything will be all right, otherwise there may be some problem. So this is so what is the other way? Well, then you have to go back to the what I have been telling, that you have to look at the 2 equations basically, right. So in this case, what will you do? You will look at the 2 equations, 2 lines basically. So one line is going like this one, yeah, and the other line may be this line. Yeah. So, that means if you know what is the, first we make this equation. So, this will be equal to say this equation and multiplied by this line, you know. So, that makes it equal to 0. So, accordingly we can write, we can go like this one. We can say n1 xi eta is equal to what is the equation of this? Okay, what is the equation of this? Equation of this is nothing but this, if you say 0 basically. Yeah, so this will be xi plus eta equal to 0. So, because if you see here we have 1, we have 1 minus 1, you have here minus 1 1, you have 0 0. So, xi plus eta equal to 0. So, this is what the equation is, right. So, this is xi plus eta equal to 0. So, that means we can simply have here xi plus eta, okay. This equation we are writing equal to 0. So, minus 0 equal to 0. So, xi plus eta we are writing, and then we have xi here. So, we multiply this one is xi plus this one is xi equal to 1. So, xi minus 1. So, you get here xi minus 1. Okay, and then at here the value has to be 1. So, what we get, this is minus 1 minus 1, right. So, this is minus 1 minus 1. So, you put here value here minus 1 minus 1. So, minus 2, and then we have minus 1 here. So, minus 2 multiply minus 2. So, 4, so 1 over 4. So, we get 1 over 4. Now, you can see here, now it is what you will get is xi square plus xi n, right. So, you will get all the degree will, I mean the order of the polynomial will be confined to this. Yeah, so we will have these terms only. So, automatically you will see equal to 1 over 4 xi square, then you get plus xi eta, right, then you get minus xi minus eta. Yeah. So, we have second order system. So, that is good. Yeah, so we have second order polynomial. So, now this we can extend, actually accordingly you can find out n2 in this case. N2 will be, for if you are going to find out n2, you have to take this line, this line and this line. N3 you are going to find out, you have to go into this one and this one and this line. N4 you are going to take this line and this line. So, automatically you will see that you will get all the values. Okay. So, this is the way. Okay. So, in this case what you have seen, instead of getting this one x y, like we are capturing this xi and eta actually. So, y square we have not got. So, if you want to capture y square and not capture this one, then we have to think differently. So, let us say you did not want to have xi eta, then what to do? Then you know that if you are here, you need to capture this. Yeah. So, if you are here, we need to capture this one. So, if we have this one, we have xi times eta. Now, you don't if you don't want to find out xi times eta, then here we should not have xi and we should not have xi and we should not have eta in this case here. Yeah. So, will that is is it possible? Probably it may not be possible. So, or it may be possible if we have something like this. Maybe we take this line, say this has xi plus eta equal to 0, here it will be xi plus eta equal to some other value. So, we can take a line parallel to this one. So, in that case we get xi plus eta, will be xi plus eta or some equal to some value. Okay, so I think it will be 2 xi plus eta equal to 2 because this is 1 and 1. So this equation will be xi plus eta equal to 2. So xi plus eta minus 1. So what we will get? We will get xi plus eta square minus 2 xi minus 2 xi times minus eta, this kind of term. So we may have different kind of equation, you may see that. So what I am saying is there depending on your choice you will get. So if you have two equation like line of the equation, if you choose like this one, this multiplied by this one, you get different equation. If you get like this, you have different equation, and so on. So so you can construct I mean there is more than one answer. That's what I mean to say. Yeah. Okay. So let us similarly, if you have like this, say like this one. Yeah. So in this case also, how will you construct? We will take two line. Let's say we are talking about this this one at this one. Let's say you are talking about 1, 2, 3, 4. Yeah. So say here. So then your line n1 you want to find out, your line will be, so you have one line which will be this one line, you are going to take this one. Yeah. Second line you are going to take this one probably, right? Yeah. So probably this will work. So automatically this multiplied by this, but if you have to see the order, so accordingly the depending on your choice, the your order will also I mean instead of xi square, if you don't want, you want eta square only. So these all things can change basically with this choice. So other will be something like this, could be one goes like this one and the other goes like this one. In this way also it works. Yeah. So you will see that still a 2b equation, you are multiplying this minus this one, so it will work that way also. Yeah. So accordingly you can compose. Okay. So your choice either this and this will have different. So in one case, for example, as I said earlier, it could be xi square will be there. In one case xi will be not there, eta square will be there, so yeah, so on. But your way, your effort should be to minimize it. You should have the minimum number of the order should be minimum basically. So for example, if you have 5, so you know that as long as you are within this one, I think it's fine. So either you have xi square eta square, or xi square xi eta, or xi square eta square xi eta, but not all. So you should have only 5 of them. Yeah. So not like you have 5 noted and you have all the 6 you are using, probably that's not a good way. Yeah. So okay, so that's what I meant to say. So similar thing applies here. So this is just to see how you can get all the shape function basically, that's what I mean. So in this case, as I said earlier, you know that this equation, let's say this eta equal to 1, this equation will be, here it is 1 minus 1, this is, so and this one will be minus 1 0, let us say. Yeah. So the equation this will be eta equal to 1, and this equation is, what is the equation of this one? So we have this minus 1 0, and this one is 1 and minus 1. So the equation is 1 minus maybe this is 2, this equation may be probably xi plus 2 eta equal to minus 1. Yeah, so you can see that xi plus minus 1 plus 0 equal to minus 1, in this becomes 1 minus 2 equal to minus 1, so it goes like this one. So accordingly, in this case n1 xi eta may be given by xi plus 2 eta plus 1 multiplied by eta minus 1. So we can see that here we have xi eta term, eta square term, yeah, and not there is no cubic term here, so this works. Now here this is minus 1, so you put minus 1, so you have minus 1, minus 1, so and this is also minus 1, so minus 2 multiplied by, and this is minus 2 multiplied by minus 2, 4, so 1 over 4, so we get n1 equal to this. So this also works here. This one similarly, if you chose this one, then you have to be careful. Here also it works, and how it works. So you can see that this equation will be this is equal to xi plus eta equal to 0. Yeah, so and this will be, since this is minus 1 0, this is 1 1. Yeah, so the equation will be similar kind of equation that will be here in this case, and we can say this is xi plus 2 eta equal to minus 1. So in this case will be eta probably minus, it will be, so xi minus 2 eta equal to minus 1. So maybe this one will be xi minus 2 eta equal to minus 1, maybe something like this. Okay, so we can check it. Here it is satisfied. You can see here, if you put 1 here and minus 1 here, so you can 1 minus 3 equal to minus 1. Here if you put minus 1 minus 0 equal to minus 1 only. So this works. So we can, in the second case, in this case, what do you get here? You will get n1 xi eta equal to, and then you have xi plus eta multiplied by xi minus 2 eta plus 1. Okay, what we see in this case is we have all kinds of things. We will have xi square, eta square term, xi eta term. Okay, so probably we will have all of them. So xi square minus eta square, xi eta minus 2 xi eta for xi eta. So all terms are there. So that means this is not a good idea, because this is going to give you all of the 6 things, basically 6 combinations. So it can be by its own. There is no in this case what you see, there is no constant term. Yeah, so in this case what you are getting, in the second case you are getting there is no constant term, but you will have this term, this term, this term, this term, this term. So you have this term basically. Yeah, here also, in this case also you are seeing there is no constant term. So yeah, in this case also, so in all of these cases what you are saying is there is no constant term, you have all the 5 terms like this one. but you are not getting one constant term like this, the way you wanted, like this one. Yeah, you are not getting that. So it may be possible that probably with a constant term is not possible at all. You have to take these 5 terms like this one. Instead of taking this one, you have to take all these 5. So it's possible that way that you need. Okay, so something like this. Yeah. So it's possible that whatever you are suggesting, like this one, finally it turns out that it's not possible to satisfy like this one or like this one. So in this case, if you are getting this term xi eta, xi square, xi eta, eta square, and no constant term, this is fine then. Okay. So this what is the case which looks like. In this case, it will be something like this one. Regardless of what you do, it's important that always the summation of ni has to be equal to 1. That's you have to check. It's also possible that out of the 4 you have found out, let's say you know all of them, but n5 you have to find out, let's say. So n5 you have already known the other ones, so you can say n5 equal to n1 minus 1 minus n1 minus n2 minus n3 minus n4, and then you get n5. Okay. Once you have this one, the next thing is how to integrate it. Okay, so integration in always remember what, let's say a function, you have f and you have xi, you have eta, and you have d xi d eta, right? So that's what you finally you get minus 1 to 1, minus 1 to 1. So this is very easy. We can apply Gauss quadrature. So let's say this is called I equal to this. So apply Gauss quadrature formula, and you can see I equal to first you can integrate terms of alpha, terms of xi. So this equal to minus 1 to 1, and for this one we can write as a function, right? So this will be I equal to 1 to number of Gauss points, right? So number of Gauss points, and then we can write wi, and then f xi I eta I, right? And then we have d eta. Yeah. Okay. Now the equal to, now once you have that, now we can integrate in terms of this. So apply 1D Gauss quadrature. So same thing whatever you learned in the like before the mid-sem, you can apply. So this is equal to will be another one. So another summation j equal to 1 to number of Gauss points. Yeah, and then we can have w, right? Sorry, here we are integrate in terms of xi only, so eta will not be I. We are not going to write in this I. This is just eta, like this one. And now we are integrating this eta, yeah, like this one. So now it will be this will be equal to I equal to 1 to n Gauss points, then w j w I f xi I eta I, like this one. Yeah. So this is how we can do, like in 2D we are treating 1D like we take xi and eta at a time and treat it as 1D, we integrate it in one dimension, then we integrate in the second dimension, what we get is something like this one. So basically, if we know that in 1D, if it is 1 point, if np equal to 1, then you know that w equal to 2, right? We know that w equal to 2, that we get, and we have xi 1, so we have minus 1 to 1. So we get xi, right, xi equal to 0. Yeah, so in that case simply if you apply this one NP equal to 1, simply we can write just there will be only one. So what we get here, Wj, this will be only one, so you have a W1. So basically here we have W1 equal to this and xi1 equal to 1. So I value will be simply W1 equal to 2, so 2 multiplied by 2, and then we will have f xi1 equal to 0, and then another one is also like minus 1 to goes to 1, right. This is xi, this is eta, so we have 0 0. Yeah, so we put equal to 4 f 0 0, simply this will be I. Yeah, if NP equal to 2, okay, if number of Gauss points, sorry, this NGP, okay, so number of Gauss points equal to 2, and then what we have, then we know that W1 equal to W2 equal to 1, and xi1 xi2 equal to plus minus root 1 over 3, yeah, equal to 1 over root 3 basically, plus minus. Yeah, so in that case what happens, our I will be equal to, now we have to add them together. Yeah, so we will have 4 points then, so this is xi eta system. So we have xi, we have eta, and then we get 4 points, okay, like this one, and those 4 points are, so we can see that, so this will be minus 1 over root 3, minus 1 over root 3, this will be 1 over root 3, then minus 1 over root 3, this point will be minus 1 over root 3, 1 over root 3, and these points will be 1 over root 3, 1 over root 3. Yeah, so this I will be in that case will be simply 1 over, so this is the value of this one, these are the points, these are the coordinates of these points, and we have to W1 W2 all are same. So basically if you look at this, what is the meaning of this, we have 1 W1 W1, W2 W1, W1 W2, W2 W2, and we have to do like this one. Yeah, where xi1 so basically there we have this value, and xi eta also the same value, right. So we have this like this, and also we can write here also we have xi 1 eta 1 eta 2 equal to plus minus 1 over root 3, this also we have. So we have this one, you put all the 3 in this equation and you can find out the integration. So basically what it turns out to be, this I will be equal to simply W1 W2 all is 1, so I will not write 1, so I will just enter the so f, it will be like f 1 over root 3 minus 1 over root 3 minus 1 over root 3, so this point plus f 1 over root 3 minus 1 over root 3, so find this one, plus f 1 over root 3 1 over root 3, so this is find this one, then plus f minus 1 over root 3 1 over root 3, and this is find this one. So we get I simply just by adding the value of this function at this 4 point. That's it. Okay, so basically what we have seen is we are just extending the one dimensional to two dimensional. So we have to integrate twice. One we integrate in x direction, another we in y direction, and we are done with that. Okay. Now in case of triangle, now similar thing can be applied, like as far as the construction of the shape function is concerned. Yeah. So we can extend, like any arbitrary triangle, we have seen that can be converted into the this kind of system. Yeah. So we have xi1, xi2 system, we have from x and y system from there. And here let us say we have the fourth one, 4 node like here. So we know that there will be 4 node which will be here somewhere. Okay. So let us say this is at the centroid. So you will also, in this case also, it will be at the centroid basically, and there will be some relationship accordingly. Yeah. So so basically what we want here is how to construct a shape function for this one. Yeah. So we can use the triangular system, like we said, this is xi, eta, and this xi1, xi2 and xi3 system. We can also, you know that the value here will be xi3 equal to 0, and here will be xi3 equal to 1 at this point. So we can construct this one where we know xi3 equal to xi1 1 minus xi1. So we know that we can write xi3 equal to 1 minus xi1 minus xi2. So this system also we can have. Now if you want to find out what is the shape function for this one, yeah, so again let's say this, let's call it 1 2 3, here 4, and we have to find out for n node 4, n4, let's say we have to find out. Okay, so once we have transformed here you can easily we can, let's say for node of a, f equal to half and half. This is the node. So this is the coordinate of this node. Okay. Now what we see here is the equation, this line and this line, the nodes are, all the 3 other nodes are on this line and this line. So xi1 equal to 0, xi2 equal to 0. So we can, straight away we can see that n4 will be most likely be xi1 and times xi2. And of course at this point when you have half and half, that makes 4, so you have to multiply 4. So you know that n4 will be equal to this. Rest other you have to find out. So how we'll do that? So in this case maybe we'll take this as a line. Yeah, so maybe you can take like this. This is a line. Yeah, so this line is xi1 equal to half. Yeah, and this line is xi2 equal to half. So we can take either this and that, anything. So we have let's say n1, if you want to find out n1, so how will you do it? So for n1, so there are 2 lines. So one line is this, another line is this one, or this one, either of the 2, either this or that. So other is also possible, you can also do like this one, but this will be a complicated one. So you should always simplify it. So n1 you will take this is xi, this one is, you know that this is xi3 equal to 0, right? So we have studied. So this one is xi3 equal to 0. So we can write that. So we have xi3, and this one is xi1 equal to half. So multiplied by xi1 minus half. That's it. So this is what the equation is of n1, and we can say that when we have 0 0, yeah, so when xi1 equal to 0, xi2 equal to 0, or when have xi3 at this point, xi3, what is the value of xi3? Xi3 is 1 at this point, right? So we know that. Yeah, so xi3 is 0 here, xi3 is 1 here. So this is xi3 equal to 1. So you put 1 here, xi1 is xi1 equal to 0. So 1, 0 here, so becomes minus half, so you write minus 2 here. So we know that the value will be minus 2, like this one. Yeah. Okay, so what we see here, we see xi3 multiplied by this, and which will be equal to minus 2. Xi3 is 1 minus xi1 minus xi2 multiplied by xi1 minus half. So you get a shape function like this one. So n1 you have got, n2 accordingly you can find out, n2 you can find out this multiplied by this. Yeah, so you can also have this multiplied by this one, so that you don't have these square term. So depending on what kind of shape function you are looking at, accordingly you can do. So for this one you looked at this one and multiplied by this. Yeah, for this one you can have this multiplied by this, for this one you can have this multiplied by this one, for this you have this and this, and accordingly you can find out. You have to check though at the end all the summation has to be, so that you have to check. Yeah, so it's very important that all the shape functions should add to 0. But this is in general how you should attempt at finding out the shape function. Yep. Okay, now this one thing you will face is how to integrate. Like once you have this n1 and then you are finding out k, and then you have to integrate. In order to find out k, you have to, like k you have some function, you will get some function here f, will be xi and eta, and then you are going to integrate basically, right? Okay, so this will be written like d omega, right? So like where omega is the original one. So again remember this, either we wrote like this one, this which is a function of xy, and then I said this we have converted into omega xi eta system, and this f. So in fact this will be a function x here, so write this x and y, this function x and y, and this we are converting into xi and eta, not xi and eta, xi1 xi2 system. So xi1 xi2 system, so f xi1 xi2, and then there will be a j, right, which is also je, and then we have d omega this xi1 and xi2. So we convert like this one. Yeah, so either, so what is the meaning of that? How to find out basically? Yeah, so we look at like this one, we said the meaning of this will be this equal to, you can write it like this, and will be 0 to 1 minus xi1, and then 0 to 1, and then if you have f xi1 xi2, right, then d xi2 d xi1, we have to multiply it by je, which is function of xi1 and xi2, and then we have d xi2 times d xi1. So this is how you do basically. So you have the whole thing here. Let's call this one from here to here as z xi1 and xi2. Yeah. Okay, so if you have this one like this one, then how to find out? Okay, so if we use this kind of system, then we have to find out this I. Okay, so in general, let's not call k, let's say in general we have I, which will be of this type. So how to integrate that? We can solve this with two methods. So let's talk about the first one, and we will apply So, the Gauss method, the way we did earlier. So, let us say this is equal to I equal to 1 to number of Gauss points. So, Gauss quadrature for triangle we can use which will equal to Wi and F xi 1 I and xi 2 I. Yeah. So, okay. So, this will for G equal, okay, you have to write G because we are talking about the everything will be like this one. Okay. So, this we have to find out. Okay. So, how does it work? So, this is this is Gauss quadrature for triangles. Okay. So, how to do it? So let us say we can let us say G is of this form, G xi 1 xi 2 is equal to a constant. So, let us say alpha plus beta xi 1 and gamma xi 2. This is like this one. Yeah. So, then what happens? Then our value, if we integrate this one, say minus 1 to 1, sorry, minus, not minus. So, the I will be equal to 0 to 1 minus xi 1, then 0 to 1, and then we have alpha plus beta xi 1 plus gamma xi 2, right. So, then d xi 2 d xi 1, we have like this one. So, what do we get? We get from here we can say this, we get alpha then xi 2 plus beta xi 1 xi 2 plus gamma xi 2 square over 2, right, and then we get 1 minus xi 1 0 0 to 1, and then d xi 1 is equal to 0 to 1 alpha 1 minus xi 1 plus beta. So, xi 1 minus xi 1 square plus gamma over 2 1 minus xi 1 square. Yeah, that is what we get d xi 1. Yeah. And then we get from 1 this will be equal to alpha and then 1 minus xi. So, we get xi 1 minus 1 xi 1 minus xi 1 square over 2 plus beta, then we have xi 1 square over 2 minus xi 1 cube over 3 plus gamma over 3, yeah, and then we get 1 minus xi 1 cube over 3, and then we get minus 1 divided by minus 1 as well. So, that is what we get, and then we have 1 to 0. So, this should be 2, okay, we have 2 here, so like this one. So, what looking at this one, if you see that if we put 1 here, so we put 1 minus half, so we get half, alpha over half, so we can keep on writing. So, this is I equal to alpha over 2, then plus, then looks at beta becomes 1 half minus 1 over 3, so becomes 1 over 6, so beta over 6, okay, plus and then we see here if you put 1 here, this becomes 0, okay. So and then if you put the value here, okay, so we get 1, Okay. So, 1. So, this the value of this is this at 1 minus this at 0. Okay. So, this the whole thing at 1 is 0, the whole thing as 0 is put 0 here. So, we get 1 1 here. So, minus 1 over 6. Okay. So, minus 1 over 6, so we get plus 1 over 6. Okay. So, we get gamma divided by 6, gamma divided by 6. Okay. Okay. So, we have that integration, we get that. Now, we know that we are going to apply the Gauss quadrature formula, and let us say we are let us decide NP NGP equal to 1. Okay. So, if NGP equal to 1, then we will have simply W1, and then we will have multiplied by F, and then we have xi 1 and xi 2 1, right, which is equal to W1, and then we have alpha plus beta beta xi 1 1 plus gamma xi 2 1. Yeah. So, if we compare this to this, how do we find? We find the coefficient of alpha if we equate. So, W1 has to equal to half. So, W1 equal to half, we got to know. Then if W1 equal to half, this beta, if you see here this, the beta over, so this one will be equal to what? This one, this multiplied by this will be 1 over 6. So, W1 multiplied by xi 1 1 equal to 1 over 6. So, that means, so that means xi 1 1 equal to 1 over 3, and similarly W 2 xi not W2, W1 only. So, W1 xi 2 1 equal to again 1 over 6, and that makes is xi 2 1 equal to 1 over 3. So, this is what we get. We get if 1 point integration, 1 point integration, we get W1 equal to half, and xi 1 is equal to, so xi 1 equal to xi 2 equal to 1 over 3. Yeah. So, this is how we can do triangular. Similarly, we can do for different other like order of the system, right. So, if you have like order 2 or 3, for example, in that case we have to take more number of Gauss points. So, in this case it can correctly find out in this case. Yeah. So, we have 3 variable here, and this side also we had 1, 2 and 3 variables this side also, and hence we found out. So, in case of linear, 1 point is sufficient, it can find out the accurate one. But if it is if our z is quadratic, then we have to increase the number of Gauss points. So, basically this was just the idea basically, and now for you basically you can always refer to your book, the values are given. So, I am going to just draw a few things. So, if NGP number of Gauss points equal to 2, if that is the case, then you can have number of Gauss points 2 probably is not decided that way. I think NGP equal to 3 because you also have to be symmetric. So in that case your Gauss points will be something like this, yeah, and the points could be here and here and here. So half, half 0, half half, and you have 0 half, yeah. This is xi 1 and xi 2. So these are the Gauss points, okay. So you can have these are the Gauss points, okay. This is Gauss points, okay, and the corresponding weightage is 1 over 6. So summation of weight, as you know, in this case weight was equal to half. So summation of weight will be half basically, and W1 equal to W2 equal to W3 equal to 1 over 6. So that you sum them, all the 1/6 multiplied by 3 is equal to 1 over 2. So W1 is this one, and this is the Gauss points. Yeah, so this can in this case you can say that this is how many variables will be in that case. You can see that. So we have 1, 2, 3, right, and then we have these points, right. So 1, 2, 3, and then 4, 5, 6, 7, 8, 9. So we had 9. We have 9 variables in this case. So W1, W2, W3, there are 3 variables from here, and then we have xi 1, xi 2. So 1, 2, 1, 2, 1, 2. Yeah, so total 9. Okay. So so total 9. So how many the kind of polynomial that it can integrate correctly, that will be something like this. So accurate for polynomial with 9 variables, okay. So let's look at, let's say G xi 1 xi 2. Let's look at the quadratic one. Let's see how it goes, okay. So let's say this is I will write as alpha naught plus alpha 1 times xi 1 plus alpha 2 times xi 2 plus alpha 3 times xi 1 square alpha 4 xi 2 square plus alpha 5 xi 1 times xi 2. So what we see is with number of variables here is basically, if you see this value will have one term here, 1, 2, 3, 4, 5, 6. Yeah, so this is a quadratic in 2-dimensional, and there are 6 things this side, yeah, and this has to be matched. Like if we integrate this one, we will integrate this one, we will have the, so if I have I equal to integrate like this, 0 to 1 minus xi 2, then 0 to 1, and z xi 1 xi 2 d xi 2 d xi 1 will have 6 variables, right. So from where alpha naught to alpha 5. There are 6 of them. Okay, and here we are seeing that this will have 9 of them. So, 1, 2, 3, 4, 5, 6 and 3 here. Yeah, so that means what we see here, that if we apply 3 Gauss points, then this is not unique, meaning that we may have different combination of this and these points to find out the exact solution of this. So, the exact solution of a quadratic equation, for example, can have in different ways basically. Yeah, how different ways? This is not a unique one. So, we can also have like this, something like this one. So, there are many ways. So, one of the way can also be something like this, one here, one here, one here, okay, where these coordinates are given by 1 over 6, 1 over 6, 1 over 6, then this is going to be this one is 1 over 6, this is 2 over 3. So, this value will be 2 over 3, 1 over 6, and similarly this one is going to be 1 over 6 and 2 over 3, like this. Okay. So, and then these are the nodes, these are the points, the integration points. So, these are the integration point. Points, and W1 we can have W1 equal to W2 equal to W3, we can assume that to be like this. Yeah. So, if they are W1 W2 is 1 over 6, we can have this combination as well. Yeah. So, there is a different way of doing it. Why? Because you have more freedom here, you have 9 degree of freedom in a way, you have 1 2 3 4 5 6 7 8 9, and there you had only 6 variable that side. So, it is easy to match in different combinations. So, this is one of the combination. So, you can refer to your book to find out this one. Okay, there is another way of calculating the area. Okay, so and the general equation is also given something like this one. So, if you have something like this 0 to 1 minus xi 2 1 0 to 1 z xi 1 xi 2, yeah, and d xi 1 d xi 2 d xi 1 can also be given in terms of so let's is also is can be got from some kind of let us say this if you expand by expanding, this will be of this type 1 minus, and then this is polynomial. So, this will be have different combination, right. So, it can have like say 1 like we wrote, it could be like this one alpha naught plus alpha 1 xi, yeah, or maybe the summation different like xi 1 plus alpha 2 xi 2 and so on, right, and then d xi 2 d xi 1. So, basically if we know individually, if we can integrate, others we can integrate easily. So, there is you can use this formula, this is also given in your textbook, and this is something like this. So, if this is 0 to 1 minus xi 2, 0 to 1, and we have xi 1 I, xi 2 j, and xi 3 k, and you have to integrate it like d xi 1, d xi 2, yeah, sorry, this will be 2 and d xi 1 with xi 3 equal to 1 minus xi 1 minus xi 2, that's what it meaning. Okay, so if let us say we call this I 1 is equal to like this one, so this is equal to, will be simply I factorial j factorial k factorial divided by I plus j plus k plus 2, right, factorial. That's it. And you can actually test it. You can find out one, like let's say you will get exactly like this one. So let's say test. Okay, so you can also derive it. It's some lengthy mathematics, but you can easily you can derive all those things. So test, let's say we call j equal to 0, I equal to 1, j equal to 0, k equal to 0. Yeah, so then we have I1 is equal to 0 to 1 minus 0 to 1 minus xi2, yeah, and then we have xi1 only, yeah, so d xi2 d xi1, then what you get is equal to, now we have to integrate this one only, so we get xi1 minus, so we get simply 0 to 1 xi1 1 minus xi1, sorry, this should be not xi2 but xi1, this should be xi1. Okay, fine. Then d xi1 like this one. Okay, so will be equal to 0 to 1, yeah, and then we have xi1 minus xi1 square, so xi1 minus xi1 square d xi1 is equal to xi1 square over 2 minus xi1 cube over 3, and then 1 0, and 1, and then what do you get? You get 1 over 2 minus 1 over 3, that's it. So you get equal to 1 over 6, which is equal to what? I factorial, so I factorial is 1 factorial over I is 1 plus 2, right, factorial, so which is equal to 1 over 3 factorial is equal to 1 over 6, so this is correct. Yeah. Similarly you can find out for all others. You can take I equal to 1, j equal to 1, and you can check. So even for full this one also we can check. Yeah, so the integration, lengthy integration, yeah, just analytical integration you can apply. You can actually derive this equation very easily. Yeah, so but this is how it works. So this also you can have this one. Mind it, this is with xi2 xi1 which is like this one, and the value we have here which has the Jacobian included here. Okay, this has the Jacobian included. Yeah, so so if you have a function like this one, C. So okay, so look at this one. So this G includes the Jacobian, the determinant of Jacobian. So remember the function, whatever you are going to use here it should have the whole thing here. So, this original function multiplied by the Jacobian as well. So, including the Jacobian has to be there. So, G is like this one. So, that is why we have done like this one. Yeah. So, if you are we can also write in terms of this also. Yeah. So, remember we can replace this with function multiplied by determinant of Jacobian here. So, you can write Wi multiplied by f xi1 xi2 and then integration of Jacobian at xi1 xi2. So, you can also like write like this one. So, you have to be careful with this one. The G includes the Jacobian inside there. Okay, so this is how you have to integrate so in the triangular system, and this is how it's also important why isoparametric element is important. This also tells you. So, the isoparametric element has like ease of integration, and hence this is widely used, you know. So here also we can write that if you have like just like this one, if you just like 0 to 1 minus xi1, 0 to 1, xi1 I, xi2 I, xi3 I, sorry not I, this will be j and this is k, and d is I2, d is I1, we can write as I plus I factorial, j factorial, k factorial divided by I plus j plus k plus 2 factorial. So, we can write like this one. If we have if we integrate this one, instead of writing like this one, if we have like this xi1 I, xi2 I, xi3 this is j and this is xi3 k, and then this is integration over say this one is xi1 xi2 system, integration over the whole domain, and you write d, this area you are multiplying by area xi1 and xi2. Then you know that in this case your Jacobian is multiplied to this already. Yeah, that's we are writing like that. Yeah, no? So after multiply with the Jacobian, and then you are looking at this one. In this case, this will have a Jacobian inside that. This Jacobian multiplied by this one is this, right? We have studied this equal to Jacobian multiplied by this. Yeah, in that case, since you have multiplying by area here, so area should come out. Yeah, so it should be equal to, since this have Jacobian already, so you can write like this one, equal to Jacobian will be equal to area over 2 basically. Finally, if you integrate over this, the area, original area divided by area of this triangle. Yeah, so the original area divided by the area of this triangle, that's what it is, and hence we will get 2 times a, right. So what we will get equal to area of the element divided by half. Okay, so ratio. So in xy system, this is the area of the triangle. In zeta system or xi1 zeta system, this is the half is the triangle, the area of the triangle. So this divided by this one, which comes because of the Jacobian, and then you have this I j k factorial divided by I plus j plus k plus 2. So we can write like this one, or simply equal to 2ae multiplied by this one. Yeah, so be careful with that. Yeah, so here we are we have this we have not written this explicitly as Yeah, you can write here where d this d xi 1 xi 2 equal to Jacobian E multiplied by d xi the xi 2 d xi 1. Yeah, this is what it is. So we have separated that. Yeah. Okay, so that is all. Actually, we have finished all the chapters. Okay, so we in the next lecture video we will solve some example problems. Okay, so I will share the example problems that I solved in the last semester actually. Yeah, so I will just share that. Okay, so it has 2 example problems from your textbook have been solved, and that will serve as the lecture video 30. Okay, I realize I made one mistake. So here this should not be xi 1 xi 2 because this itself is, so I will write like this one. So this itself is d omega xi 1 and xi 2 as per the definition that we have followed earlier. So here this one is x and y only. So you can write it here is x and y system. So this is x and y system. So this is x comma y system. So this is x y system. Yeah. Yeah, this is okay. So this is okay. So so if you have converted everything here, okay, inside the integrand, and you have not converted this to xi eta system, then you can write this equal to simply like this one, where area divided by half you have to write. Yeah, so this is how this one. So so let me add basically. So what I mean to say final is our system earlier we wrote d omega as x y is equal to j e, right, xi 1 xi 2 determinant of that, and then we call it d omega xi 1 xi 2, where d omega xi 1 xi 2 is nothing but d xi 1 d xi 2 basically. Yeah, okay. So this is what the meaning is basically. So if you have integration of omega x y, and then we have I xi 1 I xi 2 j xi 3 k and d omega x y. So we have not converted this into xi 1 xi 2 system, then this will be simply 2 times area of the element in xy system. Yeah, area of inserts in xy system only. Yeah, so but it is already integrated, so you just have to write actual area. So AE is actual area of the element in the original xy system, and then you have I factorial j factorial k factorial divided by I plus j plus k plus 2 factorial. Yeah, so this is what we mean. Yeah, so this is we can use like this one. If you have already converted from xy system to xy1 xy2 system, and then if you have this equation like this one, then you can use this equation. Otherwise, if you have not converted, you still have in xy system, you have to multiply it by 2 times area of the original element. Okay. So sorry about that, but this is how it is correct. So I wanted you not to make mistake. Okay, so hence I added that. Okay, so that is all.